Hi guys! In this video we're going to be looking at definition of coherence, stable interference patterns, coherent and incoherent sources, and we're going to finish with a summary. So we're going to start off by defining coherence and trying to understand what it is. A stationary wave is the interference of two progressive waves travelling in opposite directions. So we've already come across this idea of setting up a stationary wave. So we can see that on the left here, we've got two progressive waves that are coming towards each other. And when these two waves pass through each other, we get interference. And the interference of these two progressive waves is what produces the stationary wave. And we've seen we get both constructive and destructive interference, depending on whether the waves are in phase or out of phase with each other. The progressive waves must have the same frequency to form a stationary wave. So the frequency of this first wave, we're going to call F1, must be equal to the frequency of the second wave, which we're going to call F2. So both these frequencies are equal to a certain value f. Otherwise, we can't set up a stationary wave. The two progressive waves must have the same frequency. To produce a stationary wave, the progressive waves must have phase relationship, which is constant in time. So each of these people here are producing a progressive wave. And when these two progressive waves interfere, we end up with a resultant stationary wave, which is what we see on the string. And we can see that over time, through the centre here, we have a fixed point of constructive interference. So what we mean by this is at this point, we always have constructive interference. So after a certain amount of time delta t passes, we went from maximum constructive interference to minimum constructive interference, but we still have constructive interference here. And then again, after another amount of time delta t passes, we again have constructive interference. So we can see that the phase relationship between these two waves is constant. For example, this means that at one point in space, the two waves are always in phase, and at another point, they are always in antiphase. So essentially, the phase relationship between the two waves remains constant, so they always have a constant phase difference. So that's what we can see happening here. So for example, this first green arrow shows that the waves are always in antiphase. And this second green arrow shows that the waves are always in phase. So even as time progresses, as we can see here, that's what we're drawing this axis, the phase relationship stays constant. So we have a constant phase relationship. So for example, as we said, this second green arrow shows the waves in phase. And we can tell that they're always in phase at this point because the waves always have the same displacement. So at this point they have the same displacement, then at this point they have the same displacement, and at this point they have the same displacement. So we can see that over time the phase difference doesn't change. It stays constant at certain points along the wave. The two progressive waves which form a stationary wave are an example of a pair of coherent waves. Coherent waves are waves with the same frequency and constant phase relationship. So that's the simplest way to describe two coherent waves. They have the same frequency and their phase difference remains constant. It doesn't change. So it doesn't mean that they're necessarily in phase or out of phase. It just means that whatever their phase relationship is, that stays constant. So now that we understand what it means to have two coherent waves, we're going to see how coherent waves can produce stable interference patterns. When two progressive waves overlap, they will interfere. So for example, we can consider the water ripples on a surface of water. So that's what we've got here. So here we've got our water ripples, which are waves produced on the water surface. And when these two waves overlap, we actually get interference. So that's what's going on here where we've circled the waves. So the two waves overlap and they interfere with each other. So this is a similar idea to what we've seen so far with stationary waves. With stationary waves, two progressive waves interfere with each other and then produce a stationary wave. So these water ripples overlap and they interfere. Coherent waves produce stable interference patterns. So for example, you can produce a stable interference pattern like this by using two dippers in a surface of water that are vibrating at the same frequency. So these are the dippers, and if they're both vibrating at the same frequency f, the two waves can actually produce a stable interference pattern. So we can see that the water dippers produce circular waves. And we can see at this point here, where the circular waves overlap, we get a stable interference pattern of the waves on the surface. Stable interference patterns contain fixed positions of constructive and destructive interference. So for example, if we consider the ripples produced by our dippers, which we can draw in here, these are the wave fronts. Because the dippers are both vibrating at the same frequency, it means the ripples produced also have the same frequency. So the waves produced here have the same frequency f. And they each also have a particular wavelength. And remember, the wavelength is the distance between the wavefronts. So for example, here we have a wavelength lambda 1, and then here we have a wavelength lambda 2. So these two waves are able to interfere with each other. So here we can see that they overlap and we have an interference pattern. So in this case, when we say there's a stable interference pattern, we don't mean that a certain point will always be a peak or a trough. What we mean is that, for example, at this point here, there will always be constructive interference. So what we mean by this is it will always oscillate up and down between a peak and a trough, but the amplitude will always be at a maximum for that wave. So in this part here, where the two waves overlap and interfere, we get a stable interference pattern. And as we said for that particular point, over time, it oscillates between a peak and a trough. So it goes from a peak to a trough, then to a peak again, and then to a trough again, and so on. So at that point, we always have maximum constructive interference, so it oscillates up and down. A stationary wave is an example of a stable interference pattern. The nodes and antinodes are the fixed points of destructive and constructive interference. So here we have a stationary wave. So we've come across stationary waves quite a lot by now, and in fact, we can see that they're an example of a stable interference pattern. Because if we remember, we have our nodes, where we always have zero displacement, and then we also have our antinodes, which are our points of maximum displacement. So at the nodes, we always have destructive interference, and then at the antinodes, we always have constructive interference. So we can see that our points of destructive and constructive interference are fixed in position. So we can see that over time, because that's what we're showing here, we're showing our stationary wave at different times, we can see that the nodes always have zero displacement and that our antinodes always have the maximum displacement along the stationary wave. So it's important to notice, however, that there can still be zero displacement at the points of constructive interference. So we can still have zero displacement at our nodes, and we can see that we have that at a time t3. But that doesn't mean that it's not a stable interference pattern, because the antinodes are still oscillating between maximum displacements. Stable interference patterns can be caused by coherent waves travelling in opposite directions or which cross at a point. So for example, when we set up stationary waves, we usually have two progressive waves travelling in opposite directions, and that's what we've got here. And they've both got the same frequency and they're travelling in opposite directions. And we say that they're coherent. But we can also get a stable interference pattern if the two waves aren't travelling in opposite directions. So for example here, we again have two waves with the same frequency, but they're not travelling in opposite directions. Instead, they meet at this point here. And when they meet, they still produce a stable interference pattern, and that's because they're still coherent waves. So no matter what direction they're travelling in, if two coherent waves meet at a point, they'll produce a stable interference pattern. So now that we understand what a coherent source is, and we've also looked at the stable interference patterns that two coherent sources can produce, we're now going to look at some example of coherent and incoherent sources. Light from a filament lamp has a range of different frequencies and a non-constant phase relationship. The light is incoherent. So if we look at the light produced from the filament lamp, we know that a filament lamp produces white light. But white light is made up of a lot of different colours of light, which all have different frequencies. So that means we've got a frequency F1 here, a frequency F2 here, F3, F4. So we don't have one single frequency of light that's produced, which means we can say that a light bulb or a filament lamp is an incoherent source. So it doesn't produce light of a single frequency. Therefore, it is not possible to produce stable interference patterns using two filament lamps. So for example, here we've got two torches, and within the torches we've got filament lamps. So because we've got filament lamps within the torches, and we've just said that filament lamps are incoherent sources, we don't actually observe a stable interference pattern between these two torches here. So there's no stable interference pattern here, and that's because we know that for light, an observable stable interference pattern would be brighter and darker spots where there's constructive and destructive interference. However, when the beams from two torches overlap, we don't see this, and that's because those are incoherent sources, so they can't produce an interference pattern that's stable. Light of a single frequency is known as monochromatic. Monochromatic light is a continuous stream of oscillations of the electromagnetic field at a single frequency. So essentially monochromatic light is light of one single frequency, which is why it's called monochromatic, because that means one colour. So for example, we know that red light has one particular frequency and it also has one colour. So the fact that it's only got a single frequency means that it only is one single colour. So for example, here are some frequencies taken from the visible region of the electromagnetic spectrum. So we know red light has a particular frequency, orange light has a particular frequency, yellow light, green light, and blue light. So all of these colours of light are monochromatic because they have a single frequency. An example of a coherent source is a laser, which emits monochromatic light. So this laser here only produces light of a single colour. So for example, here we can see we've got red light, which we've said has a frequency F1. So this laser won't produce light of any other colours, and because it only produces red light, that means the light it produces has one single frequency, so it's monochromatic. And if it's got one single frequency, that means we can use this as a coherent source. So we can therefore produce stable interference patterns using lasers. Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level physics a walk in the park.